So like last time, you have 3 prompts, 3 major topics, and then on Wednesday, from those 3 prompts, you will have 2 prompts on your question sheet, and you have to pick one and write an essay of about 700 words about that. Also, you have access to the grades, the first writing assignment that you had, and there are notes from the graders or sometimes from me. Please pay attention to those notes. In general, the grades were good, high, but in a few cases, probably 3 or 4 cases, essays were not that good. Probably students didn't study very well, or they just use their own general knowledge to develop an idea or develop an essay and write about those topics. But please don't practice that, because we will have just 2 more writing assignment, and your entire grade in this course is based on these 3 writing assignments. So the first one was a good practice. You review them, review the comments, and find out the problems, and get ready for the next writing assignment. Again, you have 3 major topics. You can handle it. We already talked about all of them. And even I gave you the sources, the chapters that you have to read, or the books that you have to read to get ready for that. PowerPoints are mainly based on those bullet points. They don't contain a whole bunch of information. In PowerPoints, you cannot find a story about those concepts. Then if you just pick bullet points from the PowerPoints and try to write an essay about those things, it will not be that successful, because you miss the narration, you miss the story. So please read the assigned readings, the chapters that I marked, and then highlight them, highlight the most important things that you find there. And then in your writing, connect them together, and first create a big picture, and then dive to the details and explain the subject. Tomorrow, you're going to have discussion sessions with the TAs. Then please talk to them. Please ask questions, how to improve your writings. This morning, I had my office hours, and I had a number of students attended, and we talked a lot. So get ready for Wednesday. On Wednesday, I'll do the same thing, teaching about 15 minutes at the beginning. And after a short break, you will have about 1 hour, 50 minutes to write a very good essay. Any questions before I start today's lecture? Nothing? Perfect. Okay, folks, last time we stopped talking about Descartes. Actually, we talked about Descartes and his role in establishment of modern philosophy and modern science. Descartes tried to fill a philosophical gap that we had after, say, the second half of 16th century and beginning of 17th century. During the medieval period, it was Aristotle who connected all explanations about the universe with his philosophy. So his philosophy was able to categorize phenomena around us in nature and universe, and then talk about these categories based on the logic that he had, based on the philosophical principles that he had. And the big part of this philosophy, which was related to physical world, was called natural philosophy, philosophy of nature. which today we call it, a big chunk of it, we call it physics. When after Copernicus, many discoveries happened, many new ideas appeared in Europe. And day by day, people discovered that Aristotle's philosophy was not able to explain those findings. Then you had a bunch of new ideas, new discoveries, but there was no philosophy to connect them to. There was not a general philosophy of everything to put these discoveries on that bedrock, like Aristotle's philosophy, which worked as a bedrock. So Descartes played this role, and he introduced a mechanical philosophy in which the universe was just matter in motion, or in a better explanation, particle in motion. So particle is in a space, it has an extension, and this extension and motion together create the entire universe. And he introduced different types of particles to make stars, planets, the space filling the universe. And he introduced a kind of mechanical universe, a universe which works based on some laws, physical laws, and obviously he was a believer, and he said that God created the universe, gave the first motion to the universe, and after that this universe is moving all the time. We will see later that other thinkers, other theologians, like Newton, you know Newton as a physicist, but he wrote about theology more than physics. And we'll see that he didn't like this idea, because what kind of universe we can have when God is outside and he doesn't interfere with everything happening in this universe. So this idea that the universe was a clockwork, uh, uh, which is called a mechanical philosophy, gives this role to God as a creator and a person who his job was winding this clock and going away. And then universe is working smoothly after that. And it actually cuts the hands of God, or remove this description of God as omnipresent from the creator. So the universe is working by itself, and you don't need the presence of God in universe. So we will see that this idea was not accepted by a good bunch of philosophers and physicists, and they wanted somehow the interference of God in natural phenomena around us. Anyhow, we go back to Descartes. Descartes uh, proposed this mechanical philosophy. He explained everything based on particle in motion, and then with by using mathematics and geometry, you would be able to just trace the motion of these particles. You can express everything in a mathematical and geometrical way. And he tried to explain everything in this universe by the action of, by concepts of particle in motion, from universal phenomena like solar systems, like the way that stars produce light, the way that comets appear, to formation of planets, the death of stars, all you can find in Descartes' philosophy, up to natural phenomena around us. How do we see? How do we feel? How do we react? What's the relationship between body and or brain or thinking material, and so on and so forth. So Descartes was a turning point, actually, from this classical medieval world that we had to modern world. His major role in philosophy was how to be skeptical and then verify everything based on your logic, based on observation, based on mathematics and geometry, just not by accepting statements from big authorities in science like Aristotle or whoever was a philosopher or religious authorities. He centered everything around human reasoning, human CPU, and how to improve this reasoning and how to judge based on reasoning and facts about natural phenomena. So this is the situation that we have in Europe in uh, uh, end of 16th century, beginning of 17th century. We had a lot of discoveries, but these discoveries didn't find way into universities immediately. Universities were doing their own job. What was their job? Just to teach scholastic philosophy. Universities were places to teach theology. They were teaching a little bit of natural philosophy, physics, a little bit mathematics, but their purpose, actually, their goal was not to educate people as a PhD in physics or a PhD in mathematics. They use these natural sciences and mathematics actually to uh, help students to understand universe better and to apply natural philosophy and mathematics to what in practical issues like making calendars, like uh, explaining uh, I don't know, the cosmology of the universe, the structure of the universe, and use science in service of religion, not more than that. Uh, what we see later that natural philosophy was in under the umbrella of philosophy. Natural philosophy, as it comes from its name, was philosophy. You talked about physics based on philosophical principles, as we already talked about Aristotle. Aristotle never performed an experiment to show how things are functioning, even about the free fall. He used philosophical principles that sublunar world is made up of 4 elements and they are layered based on their heaviness. So the heaviest object or heaviest element is the earth. Above that you have water, above that you have air, and finally you have fire. Then when you have a heavy object, obviously it should go to its natural place, which is the bottom of all these three layers of air, fire, water, air, and fire. It goes to its natural place, which is the earth. And you don't see anything about, I don't know, force, anything about how does it happen. And his conclusion was when you have a very heavy object, 10 times bigger than the other one, it is 10 times more eager to reach to its natural place. And that's why you could conclude that its speed must be 10 times bigger. We already talked last time when we were discussing Galileo. Now, what do we see here with the appearance of people like Kepler, people like Descartes, and we will see later many other thinkers in physics? We see that mathematics and natural philosophy start to merge. How? Again, back to the teachings in universities, in philosophical books, you had natural philosophy based on, say, Aristotle's physics. And then mathematicians started to investigate laws of nature, like what Kepler, he discovered that planets are moving based on three laws, planetary laws, and he discovered it not by using his pure philosophical thoughts. He used mathematics, he used observation, and then he discovered about something that's happening in this universe from mathematical side. And then little by little, people, philosophers, physicists, they reached this point that mathematics and natural philosophy, they have to develop hands in hand. So this process actually didn't happen in classical universities at the beginning. Classical universities were doing their own classical job. This happened in new homes for natural knowledge, which were what? Beyond universities. We already talked about the role of beyond education or off-campus intellectual community. You already wrote, some of you, about this in the first writing assignment. But day by day, this beyond university activities increase. At the beginning, this activity was individual, personal. Okay, I had access to books, and in my own room or office, I started to learn about these things. But later, we see that in these competitive courts in city-states in Europe, we had more centers of creativity. So this court, imagine, is Medici's court. They wanted to have the best court, very famous court, doing a lot of advancement in, I don't know, fine arts, in buildings, in making roads, in having trades, in making better ships and everything. And to do that, they needed educated people, skillful people, not necessarily coming from the universities. I was I don't know, a goldsmith, or I was a blacksmith, or I was a sculptor, and I probably was a self-educated person, but I had good skill in a field, and they try to hire you and give you this opportunity to develop your ideas and come up with new ideas. And since always keep in mind that the political setting of Europe was completely different than other parts of the world. In Islamic lands, you had a caliph or a sultan or a king just ruling a big territory, and they were able to decide about everything, about education, about the production of weaponry, weapons for their military, or any other intellectual activities or craft activities. The same thing in China. But in Europe, the political setting was completely different. You had many city-states, and they had enough wealth to support these intellectuals, these craftsmen, these engineers. And in this way, we see that out of this competition, a lot of new ideas, a lot of new technologies emerged. So these groups in these courts, or groups that were formed by union of, or by collaboration of these people who were practicing new sciences, later became great institutes in Europe. So look at the founding fathers of modern science, or founding fathers of scientific revolution. Copernicus, he was out of university. Tycho Brahe, he was out of university. He was working for King of Denmark. Johannes Kepler was out of university. He was the mathematician for the Emperor Rudolf II. Galileo at the beginning was at the university, but he had all his new ideas when he came out of university and joined Medici court in Italy. So, and many other new thinkers also, they were out of universities. What was the relationship here, which is very interesting? I briefly talked about this, that these patrons, these supporters, royal princes, nobles, they had some practical goals to have the best astrologer because they believed in astrology. So please think about this carefully, that as we spend money in NASA to send, I don't know, satellites around the Earth to make our prediction of the climate prediction power, to increase the climate prediction power of human being, or other investments that we have, they believe exactly the same way, that this guy, this astrologer, can predict the future. When we're going to have famine, when we can have, we make peace with our neighboring countries, or we start war with, I don't know, other cities state. So they believed in it, and that when they believe, as we believe in NASA, you had to spend money. Then they let these astronomers to have observatories to make a lot of tools of observations. And since they needed second opinion, third opinion, they had a number of astrologers there, a number of physicians there, let them to practice and find new ways for in astrology, or in medicine, or in, I don't know, making gunpowder. And this was the dynamics of that period in Europe. At the same time, these people gave prestige to these courts. Obviously, it was a great achievement if you had Michelangelo in your court, if you had Galileo in your court, if you had Da Vinci in your court, or uh, people like that, like you hire Descartes. The Queen of Sweden hired Descartes as her personal philosopher. And okay, Descartes is in my court. Okay, so a combination of practical goals that they had, and at the same time prestige, led these courts to hire or to bring these famous people in their courts. At the same time, these people found actually a better job there. It was a win-win situation. So you are a thinker, an inventor like Leonardo da Vinci, and if somebody pays for you, or prepares all facilities that you need, then it is really good situation that you go there and express your ideas there, and at the same time have a good life and do whatever you want. So this is the dynamism of this period, and that's why we refer to what the multiplicity of creative centers. So each of these courts were centers for creativity. Example, again, we start from Galileo. We already talked a little bit about Galileo, but Galileo, without the support, let me start from this, from a different angle. You make a telescope and you like to, I don't know, observe the stars. It is one part of the story, but there was a big need for this telescope. How? Because you could use it in military. You could have posts around, I don't know, Venice, and see who is invading you, who is coming, who is going, and you could see far distances. And to do all these things, you had to make lenses, you had to find better glasses, you had to spend time in grinding of these lenses. You wanted to make bigger and bigger telescopes. You had to study the optics of these lenses and find about the refraction, reflection laws of the glasses, and how can you survive without a support to do all these things. Like universities right now, that they support professors to, okay, teach one course, but at the same time do a lot of research. I'm paying for your research. The same thing happened in these courts, and Galileo was able to improve his what call knowledge in making telescopes. He had free time to have more observations and obviously have a lot of discoveries and analyze the observations that he had. So you have, these are Galileo's drawings. This is a full moon with a modern telescope. This is what he saw through his own telescope. And this line, which separates the dark side and the bright side of moon, is called terminator. So again, think about how genius this guy was to prove his ideas, his anti-Aristotelian ideas. Think you are a student there or a philosopher at that time, and Galileo asks you this question: what is the composition of the moon? And you are an Aristotelian philosopher, you would immediately say that it is made up of ether, and that is the most perfect substance that we know in this universe. Then it is completely smooth, because the most perfect shape in the universe is a sphere, and obviously sphere is smooth. Then he asked this question: if the moon is a complete sphere and the phases of the moon are made by sunlight, then it is simple geometry. You put a sphere here, this is the source of light, and we are here observing it. We should see this terminator as a straight line, not this zigzag line. Okay, what's your answer, Mr. Aristotelian philosopher? Okay, there were some answers. They would some claim that, okay, it happens in our upper atmosphere. Okay, because light passes through different, I don't know, layers of air or some dust, or according to them exhalations that we have there. But how it changes every time in different shapes, but after a month, you have exactly the same shape of zigzag in exact the same phase of the moon. How does it happen that our atmosphere repeats the same thing over and over? What was Galileo's answer? He said that, okay, it is simple. You can understand in this way that the surface of the moon is not 100% spherical. You have mountains on it, you have valleys there, you have craters there, and when light passes, sunlight passes through them, okay, some parts it has shadow, some parts doesn't have shadow, then you have this crooked, this rugged, terminator. Again, here you see that the terminator, this is the drawing of Galileo, and he showed obviously to many experts there, many people from high rank Venetian Senate. He invited them. There was a tower in Venice. Actually, it was ruined in 18th century and they rebuilt it. But it is a very tall tower, and he asked all these old people to climb the tower, and there he uh, showed these phenomena by his telescope. And there you observe that this is a zigzag, rugged, what called line, terminator. And then when Galileo started to explain it, then little by little, people started to match the observations with geometry, with mathematics, and then find out that the surface of the moon was not smooth. This image that you see here is obviously with modern telescopes from space probes, actually, when they approach the moon. But you can see similar uh, what similar effect of shadows and passing of the sun rays through valleys or shadows created by high mountains, and it all these create what the uh, uneven terminator. Galileo was so smart that using the geometrical arrangement of the moon, the earth, and the sun, and the length of the shadows, he was able to calculate the height of the mountains on the moon. Remember, we already talked from Kuhn's book that they were able to find out about the ratio of the moon to the size of the earth, the ratio of the size of the sun to the size of the earth, though that ratio was not correct. But using that ratio, he was able to calculate the height of these mountains. And again, mathematics, observation, new ideas about the universe. And this practice was not the practice of natural philosophers. Now we are in a period to introduce a new way of practicing natural philosophy. The same thing happened in the field of medicine. I mentioned one here. We already talked about Andreas Vesalius. Vesalius started a new anatomy, though his idea was completely based on Galen. Okay, so his attempt was to create a modern version of Galen by having very accurate measurements, by having very accurate observation of human body and human organs. And for the first time, he created a very realistic book of anatomy of human being by dissecting, by analyzing everything he found in human body, from circulation, vessels, to nerves, to layers of skin, to layers of the components of brain, and so on and so forth, and dissecting of heart, dissecting of the abdomen, and so on and so forth. So it was a new approach how to incorporate very accurate and measurement-based observations in medical studies, in anatomy. You cannot find this in pre-modern era at all. They had a general idea that this is, I don't know, eye, and the eye works in this way. This is liver, this is intestine, and that's it. But Harvey started to continue Vesalius' approach to have a very accurate and measurement-based observations. So observe this. Okay, we have veins here, and then we have this we have pressure we feel under our blood vessels. Okay, sometimes we see that the pressure is high, sometimes it is lower. Sometimes you see that vessels are visible on our hand or body, sometimes not. And this was a beginning of a study of what, an experimental study of these vessels, what's going on inside that. If you remember, I briefly talked about Galen. Uh, he did all his dissections on majority of them on apes, and since by the time that they wanted to do dissections, uh, the animal had lost its blood completely, then they were not able to find out really what was going on in the relationship between the heart as a pump, blood vessels, and or respiratory systems. Galen talks about a kind of a spirit that circulates around our body, but it was William Harvey who was outside of the university. He was uh, the physician of the King of England, and there he was started this uh, systematic observation and measurement of what pressure on our vessels. And by performing experiments, as you see here, how to control the pressure by uh, controlling the circulation of blood in our body, he was able to discover something which nobody discovered for about 2,500 years, the circulation of uh, blood in our body. Before that, a Muslim I'm sorry, not astronomer, physician, discovered the circulation of blood in our pulmonary system, but not the entire body. It was William Harvey who found this, and then a new question appeared. It is very important that this question remained an open question until the beginning of end of 19th century, beginning of 19th century, that okay, this blood circulates in our body and enters in our uh, uh, what lungs. Then what happens there? So in their own language, how this dark blood turns into red fresh blood, what's happening there. And it was a long story that they had to discover what's happening in the cells of our lungs and how we exchange oxygen and CO2 there, which happened later by the invention of better microscope. So this is a discovery in medicine happened outside of the university based on what new approach that we have in natural philosophy, which was experimentation. Okay, so he studied medicine in Padua. Padua, Italy, that time was a leader in medical studies, and then he went back to England and there became the physician of King Charles. And there he had this opportunity to do what? Experiment, to investigate more and more the ideas that he had about human body. It was not possible in the university setting. So you see that these courts, little by little, uh, acted like new institutes for the development of science. Two of these early institutes, advanced, or let's put in modern science institutes, appeared in Italy. And it is interesting, or it's acceptable to happen in Italy because we had a better what called the city state settings there. We had wealthy courts there. They started Renaissance. They hired these people and these thinkers and craftsmen and mathematicians. And there we see that one of the earliest new science institutes appear, Academia de Lynchia, the uh, the Academy of Lynxes, because this animal has very sharp eyes and is very vigilant, and they compared actually their own union or academia or institute like that, that we watch everything we observe. We are very vigilant about natural phenomena, and they hired people. They did a lot of experiments in different branches of science, and they started to do what is very important: publication. In a minute, we're going to talk about the role of this publication when we talk about other institutes, but just think about this for a moment. Who could publish that time? Though we had printing press, we already talked about these little books which craftsmen published. But in the field of natural philosophy, you had big guys, big theologians or philosophers or what's called mathematicians. Majority of them, they were publishing what? Commentaries on classical sciences. We had some new thinkers like Tycho Brahe or Copernicus or William Harvey and say Kepler. They published books, and writing books took a long time. You had to collect a lot of facts to make a volume. But now, this publication as a journal, as a fast publication, changed the nature of scientific communication. So I'm not waiting here to, I don't know, write an entire book about comets and publish it. I do an observation, I come up with a new idea, and I immediately publish about this. How can I do that? Somebody should support me. And we had this academy which support them, and they were able to publish a pamphlet or I don't know, a short article. And later, as we will see, it took the form of a journal, a scientific journal, a journal that they were able to publish monthly or bi-monthly, and so on and so forth. Then we have another Academia del Cimento, Academy of Experiment, as you see, Academy of Experiment, and it established in Tuscany. And there, again, they hired what called practitioners of modern science, people interested in experimentation, in creating new devices. And there, they practiced again from alchemy to medical studies to physics. And both, they had what pragmatic goals. If nobody knew that time, if somebody achieved to make gold out of copper, obviously it's a big achievement. Then you invest now, like buying lottery tickets. You spend $5, $10, $20, and $100, but it's not a big investment from. But if you win, then it's gonna change your life. The same thing they wanted to do. If they pay to these people and they invent a better navigation system, they better find and make a better telescope, or make better porcelain to sell them and make money out of that. So all these things were combined together, scientific research, at the same time practical goals, which flourished actually a lot of activities in this period. Now, what do we see in this period? say in 17th century, starting from the early decades of 17th century and after the second half of the 17th century, we see that three categorically different scientific institutes appear in Europe. What kind of scientific institutes? One major scientific institute covering all sciences, mostly physical and experimental sciences, or they called it physico-mathematical experiments. How to do experiment and find out about mathematics behind the natural phenomena. There, they covered majority of the fields that we have, scientific fields. Then we had another institute covering astronomy, because by the invention of telescope, they had to use telescope the best in their observations, and the setting of classical observatories were based on naked eye. Then they had to change it from making bigger and bigger telescopes, the establishment of telescopes, the dome that later they appear to, how to cover the telescope, or how to equip their naked eye instruments with telescope. This is the concept of modern observatory. And then the third institute, the third type of institutes, was botanical gardens and museums. Why botanical gardens and museums? They mostly spent time on research on life science, on biological science, not medical, but life science and biological science, in this way that 16th, 17th, 18th century were what the period of great navigations, the period of discovery, and Europeans were able to travel everywhere on the globe and come back with thousands of new species, thousands of forms of flora and fauna. And there, they had to study all these things. They had to find out the relationship between these things. So you travel to a remote island and you find, I don't know, a bird there. Oh, no, bird can fly, but let's talk about, I don't know, a kind of horse you find there, or a kind of dog you find there. Then the question was very clear. How did life appear so similar to each other in these remote islands without any connections? In some islands, you find flora and fauna which you cannot find in other parts. Then how did they develop? I'm not talking about evolve there. It was a very important question that time, that what's the connection between them? So they created in one place and then spread. And since, again, the baseline, the stratum, the bedrock for all these all these ideas was the religion, then they had to connect all these findings with general concept like flood. So they believed that flood happened on the earth, and then the entire earth was covered with water, and Noah took pairs of animals to his ark. Then the question was this: you find different species all over the world. Okay, he took the prototype of dogs there, all breeds of all types of dogs to the ark. He took the prototypes of, say, you name it, okay, elephants or leopards or insects there, all types and all breeds. So acceptable and based on the script, he took the prototypes. The question was a genuine question. Then how did all the diversity that we see appear later? Based on the Bible, the age of the earth was about 6,000 years. So a very simple study shows that to have this diversity of hundreds of types of dogs or other insects or animals uh, needs a very, very long time. One of the first questions that appeared after all these geological studies and studying of the globe itself was about the age of the earth. Okay, I don't talk about it about more because uh, it goes to more details, but all these questions about evolution later we will see which uh, what appeared in Darwin's studies started from these botanical gardens, started from studying of variety of flora and fauna in the entire globe, and by finding, for example, this is also a time that mining developed a lot, geology became a science, and then they found a lot of fossils. For example, they found bones, a very big bone, which you cannot find any animal living on the earth having such a great bone. And they came up with this conclusion that, okay, once in the history of Earth, we had animals that we don't have it right now. What happened to them? And you find different types of fossils, and you find connections between similarities between them, and then you think about kind of change in living stuff on the earth. What caused this change? And it is the story of what later became what theory of evolution. These are the most famous scientific institutes that we had in Europe from mid 17th century. The first one was the Royal Society of London, which was established in 1616. Actually, it was a union of scientists. They practiced modern science. They had root in universities in England. But they wanted to do more. They wanted to enter into what practicing of these modern ideas and modern science. Then they established this the Royal Society of London, and there for the first time we see that they had a big lab, and they hired a lot of experimenters there. So these scientists, philosophers, they were noble people. They did never touch these, I don't know, lab equipments. It was beneath them to engage in such and such things. They were to make their hands dirty. So they hired people and asked them, okay, mix this with this, or do this electrical machine, and then perform such and such experiments and give us the results. And it was very, very fruitful. And they published the first scientific journal in history of humankind, which was the Philosophical Transactions of the Royal Society of London, which was published in 1665. I encourage you to go to the library homepage, and there under databases find JSTOR, or you can directly go and find this Philosophical Transactions of the Royal Society. For hundreds of years, you can have free copies there. You can go through pages of that, and it is amazing. It is so interesting that when you read this journal from 350 years ago, you find that people or the scientists, these investigators, they travel, I don't know, to a new world. They find a new snake there, like rattlesnake, which was not native of Europe. They start to study it carefully about the patterns of the body, the skin of the skin, about its shape, about the rattle that it has in the end of its tail, length of different rattlesnakes, and which one is male, which one is female. Studied their what do they do in the mating time, and many things like that. And you see that this is a new approach to learn about nature, how to do observations and report them. Or I remember there was an article from a navigator in eastern parts of India. That time they traveled there. And the reporter had that time very new measurement tools, like to measure approximately the temperature, because it is again a longer story that thermometers evolved in a long time, because we had to wait for developments in making of better glasses, very thin glasses to fill it with alcohol or other stuff. But the original thermometers were very big. And they had barometers, how to measure the pressure, how to measure or guess about the humidity, or guess about the direction of the wind and speed of the wind. You see that they tried to make a report about all these components connected to each other, and make a scientific report about climate, about condition of weather in that part of the world. Or we see that they traveled all around the world, and they found about declination of a compass, and they mapped actually the direction of compass and the orientation of a magnetic needle around, and many things like this. And each month, in each issue, they had a lot of new ideas. And at the same time, what makes it so interesting, that you publish it, it was Thomas Hobbes' idea, talking about this, that you have to make your scientific argument, scientific method, your discoveries public, that everybody could see it, discuss it, communicate with you, criticize you, and establish a scientific dialogue. And we see it exactly here. They publish about, I don't know, something, light acts like this, then another philosopher, another physicist communicates with this journal. Based on my idea, this part was not correct, this part was correct, and then you establish a scientific dialogue, which immediately helps the improvement of the scientific ideas. And at the same time, it creates a race, it creates a competition, who come up with new ideas, new experiments. Obviously, people like to be famous, and this fame definitely brought them good appointments, good salary. Like now, you have a good resume and you can find better jobs, or you can get Nobel Prize. Then you see the beginning of this scientific competition and this dynamism in this period. The second institute established in Paris, the Royal Academy of Sciences in Paris, and they started the publication of their own journal, this Memoire de l'Académie Royale des Sciences, or the Memoirs of the Royal Academy of Sciences. Uh, this Royal Academy actually was created by the government. Uh, the Prime Minister of Louis XVI, Colbert, believed that if we use science, we have more progress, we have more civic progress, we can make the country more powerful. And they, though nationalism was very important at the time, or became very important later. So in England, people followed Newton as their hero, national hero. In France, they followed national heroes as Descartes or later Laplace or other philosophers and physicists. In Germany, they followed, I don't know, Leibniz. But specifically, this Royal Academy of Sciences in Paris had a kind of international nature. They hired people from all neighboring countries, from I don't know, Netherlands, from Germany, from Russia, and they created an intellectual atmosphere there, which many new ideas appeared there, many new experiments, new discoveries, which you can follow it again. You can find this memoir to the Academy online, and if you know French, you can read it. Then botanical gardens, many botanical gardens you'll see in this list appeared, like Jardin du Roi, which was the garden of the king in Paris, the Royal Garden at Kew in London, which uh, uh, is still one of the greatest institutes of botanical studies that we have in the world. And I assure you, if you go there, this gardens at Kew, if you are very interested in this field, you cannot finish it in, say, 5 days. Every day you have to go there, a full day, to see all of what sections of this royal garden. And also the same thing about observatories. Paris Observatory, modern observatory using telescopes, established in 1672. Royal Greenwich Observatory, 3 years after that. And then we will see that this Greenwich Observatory became the leading observatory in the world. And that was so powerful, scientifically speaking, and the type of instruments that they had, that became what the reference point which they pick to establish the prime meridian. So the prime meridian passes through North Pole, the Royal Greenwich Observatory. If you go there, you see the line. They draw the line that meridian passes through there and goes to the South Pole. And then later in other parts of Europe, these new academies, new observatories appear. As you see the Royal Prussian Academy in 1700s, St. Petersburg Observatory in 1724, and in Sweden in 1747. It is also very interesting. If you are interested in this field, please communicate with me and I'll provide a lot of information for you. These modern sciences developed in a very small part of the world, actually in a small part of Europe itself. In England, it started from Italy and then moved to England, and then in France. Later, Germany involved in this process. Later, the western part of Russia, like St. Petersburg, involved in this. But the other parts of the world, they imported the science. They were not involved in all these activities that we already talked about that. So we had states, literally speaking, in walking distance to these centers of creativity. what happened to them? So, for example, the Ottoman Empire or Greece or uh, Russia itself, how much they were able to uh, understand and assimilate this new science, incorporate this new science and technology in their educational system, in their daily life. And this makes what the difference that we see right now in the development of science and technology in different parts of the world. Which one was the most successful? Japan. Japanese didn't know about all these things until 1860s. Actually, they closed their doors to foreigners from 1650s. When Tokugawa came to the power until to Meiji's. While at least in some Middle Eastern countries, they knew what was happening there. They traveled there. They learned about printing press. They translated, I don't know, Tycho Brahe's essay. They brought telescope into their countries. But what happened? This is a different story, a longer story, which I just leave it as a question. You can think about this. But if you are interested to learn more, please communicate with me, and then I provide a lot of information for them. So the Royal Academy of Sciences in Paris, which was established by Louis under the supervision of Colbert, the prime minister for Louis XIV, and he hired many scientists like Christian Huygens, one of the greatest mathematicians, physicists, and astronomers. Cassini, they were a big family. The member of this family discovered about the details of ring around Jupiter. I'm sorry, around Saturn. That's why later we called this space probe a Cassini space probe. We had Ole Romer coming from Denmark. He was the first person who astronomically established the speed of light by comparing the motion of satellites around Jupiter. So sometimes Jupiter is closer to the Earth, sometimes is away. Okay, actually we are moving faster than Jupiter. Sometimes we come closer to Jupiter, sometimes we are away. But the satellites around that are moving like a clock. You know about their circulation and their exact time of their revolution around the planet Jupiter. So when we are closer, okay, the light reaches us in a shorter time. When we are away, it takes a longer time. By comparing this, Ole Romer, before the 1700s, he calculated what? It was in mid-17th century. He calculated the speed of light, something close to the number that we have, around 290,000 kilometers per second. It was a very interesting discovery, and they published their findings in the journal, this Memoirs of the Royal Academy of Sciences, and these people established one of the largest modern observatories in Paris, which is this Paris Observatory. Here you see Colbert is what presenting the members of Royal Academy of Sciences to Louis XIV. And obviously, some of these politicians, like the king himself, he didn't know anything about these things. He was interested, but there's a famous story that time these scientists were experimenting the pressure of air. They had this idea that air had a weight, You don't feel, just again, switch your mind to 350 years ago, and somebody comes to you that are weighing the um, air. Okay. So it was so funny that uh, Louis got angry that you waste your time to weigh the air, and then what after doing that? But people convinced them, okay, let's us to do our job, and you will see that from out of all these investigations, we're gonna make some practical use. So this is the charter of the what's called this Royal Society of London. Uh, Here you see the bust of Charles II. At the left, you have William Bronker, which was the first president of the Royal Society. Who is this guy here on the right-hand side? Francis Bacon. Who was Francis Bacon? We already talked about him. The father of experimental philosophy, and one of the most important goals of the Royal Society of London was experimentation. And they actually invented a lot of instruments there. They designed instruments there. They performed a lot of experiments, and they made a lot of discoveries about science. Uh, this is the first issue of the Philosophical Transactions of the Royal Academy, the Royal Academy, I'm sorry, Royal Society of London. As you see here, this is covering this what's called volume covering from 1665 to 1666, and this is the first scientific journal in the world. Very fast medium to share your ideas, your discoveries with your peers or public, and establish a communication and what you call a dialogue between all these thinkers and philosophers. Talk about your experiments, about the details of experiments that they have and the results, and just make it available to everybody, not like alchemists hiding in a cave or their private lab, and they just do stuff without sharing this. This is a period that a kind of democratic ideas appear in what scientific activities and promotion of science to make everything available for everybody, and everybody can perform the same experiment and verify if you are correct or not. Okay, folks, how about we have a break of 15 minutes and then come back to continue? Okay.
Recording stopped. Recording in progress.
Okay, folks, back to work. Any questions? Nothing? Okay, one thing that I have to mention here is about the relationship between technology and science. How science impacts on technology and vice versa. For a long, long time, there was not an organic relationship between science and technology. We already talked about that science was doing its own job. Even specifically after the establishment of higher education institutes, universities, they just taught 7 liberal arts, and technology was doing its own job, and their knowledge came from either the secrets that they had in the family, in their guild, or some what called practical knowledge that they had about the items that they were using in technology. For example, from trial and error, they knew what kind of lumber they had to use in making of a ship hull, or what kind of stone they have to use when they are making the base of, I don't know, a bridge. So there was not a very systematic relationship between science and technology. And the only two places that they were somehow connected to each other was in timekeeping devices. To make a clock, you had to know astronomy very well. And in architecture, when you're planning, I don't know, cathedral or a big building, you had to know geometry very well. But after that, when you want to really construct this it goes to the realm of engineering and technology. But what do we see in the emergence of new sciences, the emergence of scientific revolution is the importance of experimentation. And to do experiment, you need experimental tools, and you need to design them. And here, you actually come from theoretical knowledge that you have into design process, and you enter into applied science and into technology, into engineering. Another aspect, another angle that you can look at this relationship between science and technology in this period came from some simple inventions, accidental inventions. We don't know what was in the mind of the inventor of telescope, but all story says that it was invented by accident. Even there are stories that a kid was playing with different lenses in the lens grinding shop, and he noticed that combination of two lenses can make things closer to, you can see remote things closer. It didn't come from a systematic investigation of lenses with this aim: how can I see distant objects closer? But when telescope was invented, then what happened? It created a revolution in astronomy. For the first time, we were able to see the surface of the moon. We were able to find out spots on the sun, and many other discoveries that we already talked about that. And day by day, by making better and better telescopes, we were able to see more and more. And at the same time, science helped how to improve the quality of telescope. Telescope helped scientists to improve the quality of their astronomical observations. In the field of macrocosmos, the big universe, at least for thousands of years, we knew about existence of stars, planets, uh, the moon, the sun, but we didn't know anything about the fine structure of matter. We didn't know anything about stuff below the resolution of our eyes. So our eyes can recognize, I don't know, 1/10 of a millimeter or a little smaller than that, but not more than that. But when microscope was invented, again, it is a long story, people started to use magnifiers, a combination of magnifiers, and finally they were able to make microscope, and they started to dive into a big ocean that they didn't know anything about that before. They started to see things that nobody imagined could exist in the fine structure of matter. And one of the leading scientists who he can be considered the father of microscopic investigation was Robert Hooke. Robert Hooke was a scientist, graduate from Oxford or Cambridge, I don't remember. But he studied in the university. He was one of the leading scientists in the Royal Society of London. By the way, he and Newton were enemies all the time and fighting scientifically. And he started a systematic investigation of very small stuff with his telescope, with his microscope, I'm sorry. I put a link here. Please go to this link and you will see Robert Hooke's book page by page. And you can imagine how revolutionary was his studies in understanding of, I'm sorry, the real book is here. The link to the original book is here. You can go there and find out how revolutionary was his studies of small structures. Look at these. Okay, remember that we didn't have photography that time, and you had to set the microscope with that crude microscopes that they had with the very unstable, say, base, and the way that you have to just lit this sample that you have. But he achieved to create these wonderful images of a fly, or the composite eye of a fly, and insects, small creatures. A couple of months ago, I tried to do the same thing. Okay, I have a good microscope, a professional microscope, not that crude one, and my sketching is not that bad. In my leisure time, I try to do some sketching. And believe me, after 1.5 hours, I gave up because it was so difficult to look through. My microscope is binocular. You have two eyepiece there, but the microscope that Robert Hooke used had one eyepiece. Then looking there and then sketching, looking there. But these scientists were so dedicated, and they were in an intellectual climate that there were a lot of things to investigate and a lot of things to discover. And they were able to create these masterpieces. You remember Hooke from other investigations that he had in physics. So these are other drawings by Hooke. He discovered about cell, though he was not able to find out about its importance as a unit of life. He investigated, for example, shapes of snowflakes. And again, put you in that situation and you do all these observations, then what happens? Each single of these observations create a bunch of new questions. that you have to explain, that you have to find out about the reason for that. And to do that, again, you needed more observational tools, more what called measurements, and coming up with new ideas. Uh, let me give you an example here. See what was the dynamics of that period in the Royal Society. So let me use what? Freezing of water. So when you freeze water in a closed envelope, enclosed container, it expands and it can break the walls of the container. It explodes. So it was a common idea that there is something in cold which enters into body of water. In other words, water absorbs something from cold, which adds to its volume, and it expands and explodes the container. Perfect, you can accept it. You can say based on Aristotle, based on Plato, based on other authorities, it is completely understandable that it explodes in that way. Otherwise, there's no other reason, because you see that the volume increases. But this is a period that mathematics, measurement enters into what our scientific study. We are not sitting here and just using our philosophical speculations to explain something in nature. Okay, if something enters into water and increases volume, it should be measurable. You cannot say a spirit going inside that. It is material. It is something that has a physics which enters into water and expands and causes the rupture of the container that we have. How can we measure that? Then the question, how can we measure the temperature of water in different temperatures? So one of the first experiments that happened here was, okay, you should make a very, very accurate balance. You make balance and you weigh water, a container of water, imagine a gallon of water. Okay, you know that this perfect, it's the measurement that you have is very accurate. Then put the water outside in the cold, and then it freezes and expands and breaks the gallon that you have. Then weigh it again. If something physical entered into that, then it should increase its mass. You cannot say that something entered into that. It has volume, but it doesn't have weight. That time they were able to even weigh the air that we have. So if something even as rare as air enters into that, it should have a weight. Then with over and over experiment, you find out that there's no increase in mass. Then what's the conclusion? Then cold does something with water. Then water is made up of what? We don't know. That time they didn't know. It's water. Then you can imagine that water is probably made up of very, very small particles. You see, you spray water, or you can evaporate water, and you turn it into very, very small particles. They expand, and then they condense, and they make water again. Now you think in this way that when these particles get colder and colder, probably something happens to them. They take distance from each other. And it is something internal. Something from outside doesn't enter into water to explode the container after freezing. So you see all this new type of observation, new type of scientific investigation was completely different than whatever we had before. It was completely based on what? Observation, measurement, and doing experiment, and in this way, finding something new. The idea that developed that time was by Boyle. It was uh, close to the idea that we have right now. So you have H2O, and then in liquid form, these molecules are very, very close to each other. But by definition, when you make a solid of that or you freeze that, so by definition, solid means that these molecules or atoms in a sample that you have, they take a geometrical shape with each other. So in the case of water, we see that these molecules stand on the corners of a hexagonal shape, and they need more space instead of just touching each other, coming closer to each other. And in this process, an expansion happens. The original idea, without knowing anything about molecules of water, was close to whatever we know right now. And it came from what? More observations and measurement. The same thing happened in life science. So this is the period, we already talked about that period of big journeys, discovery, age of discovery, and thousands of samples arrived in these institutes from all over the world, and they had to study them and find out about the connection between them, or define them, identify them. So in Aristotle's system, Aristotle's natural philosophy or natural history, we had categories of the known flora and fauna, but after the increase in the number of these samples, you need a new system of classification, a new system of naming of these samples that you study, their connections, find out about the relationship between them. Okay, what's the relationship between dogs, cats, lions, leopards? What's the difference? What's the relationship between donkeys, horses, mules, and I don't know, kangaroos? That time it took a while for navigators to discover Australia and find kangaroos. But the same thing in everything, in every aspects of life science, they wanted to classify them and find the relationship between them and describe them. One of the leading scientists in this field in England was John Ray. He was a natural scientist, and at the same time, he was one of the founders or leading members of what? This natural theology. What was natural theology? How to use these new new discoveries, the new science that you have, and connect it to your what religious beliefs that you have. So how to connect, again, your discoveries in nature to the divine, to the order that God created, the blueprints that God had. This is an approach like the approach that Kepler had. When you find the mathematics of the world, mathematics of universe, planets, stars, then you find what was in the mind of God. The same thing in life science. John Ray studied a lot about plants, about animals, to find order there, to find connections there between different species, and in this way prove that there was a divine design to create all these things. So again, to do this, what they had to do very accurate observations. The same way that Vesalius described the body organs, the same way that William Harvey studied the body and circulation of blood. The same thing in what flora and fauna, just find these samples, study them very well, measure everything, describe in detail, and in this way have better knowledge about the relationship between them. This is, again, the cover page of the first issue of the Philosophical Transactions of the Royal Society. And what's so interesting in one of the pages, in page 19 here, I copied and paste here, is what images of human sperm. So combine questions about heredity. Now you just invented a microscope. You can see very small things, and then you try to find out what's going on in human body in conception, and to finally find out that what happens in conception of life. So they studied sperm at the beginning with those crude microscopes. They believed that in the head of sperm, there is actually a miniature human being sitting there, which is complete human being, and it just needs to expand physically, size-wise, in dimensions. And it happens when sperm meets an ovum. So after conception, it gets nutrition from the ovum. So then question appears, okay, if everything is defined by man sperm, then how come that you get traits from mother side? How come that you have a daughter at first when everything comes from the father? Then you see that one instrument, which is microscope, opened the door in biology for many, many different branches, from embryology to cell study. And then when they started to see cells bigger and bigger, they borrowed concepts from chemistry to find out about the chemistry of cells. The same thing about the chemistry of whatever they observed under microscope, like this sperm. So this period, without any doubt, you can say that probably every week you had a new idea, new observations, new tool that people made to use in their scientific activities, and all reflected in those two journals that we already talked about. This one journal published by Royal Society of London, and the other Royal Academy of Sciences in Paris. Okay, Royal Society established in 1664. I'm sorry, 1666. And a bunch of very what's called brilliant scientists formed that. Not only they were thinking about new sciences, about this physical-mathematical experiments, they knew about the power of experimentation, but if you looked in detail in their philosophies, you could find a mixture of new ideas with a lot of classical ideas. We can start with Copernicus himself. He made a revolution in astronomy by switching the position of the sun and the earth and attributing motions to the earth and so on and so forth. But he still believed in this Platonic Aristotelian idea that the celestial region was completely perfect and everything must be in uniform circular motion. And he was not able to get rid of that idea because he didn't have any evidence. So the cosmology that he created was based on some dogma or some principles, some axioms coming from classical philosophies, and then a part of that was revolutionary, new. The same thing in Galileo. Galileo had a lot of new ideas, but some ideas that he had about, for example, comets, was way primitive than Aristotle's idea. So Aristotle's theory about comets was a better explanation for comets than Galileo. And this was a mixture of ideas when philosophies were there until we reached to a great figure of scientific revolution, Isaac Newton. For sure, if you want to divide history of science in two parts, in the entire history of humankind, definitely dividing point past Isaac Newton. He was such a great figure, which not only established this modern science that we practice, but also he created a philosophy, a kind of investigation philosophy in nature, which enabled other scientists to practice the same thing and bring revolution to different branches of science or create sciences which we didn't have before. So it is not just exaggeration about the role of Isaac Newton that Alexander Pope says that God said, let Newton be, and all was light. Because he discovered the most fundamental laws in nature. And since he was a very, very dedicated believer, he, as I repeat many, many times, that he wrote about theology more than physics, he, following the what's called philosophies coming from Kepler, for example, who said that if you find mathematics in this universe, you find you read God's mind. The same thing you can find in Galileo, that he said that God created everything in this universe with the language of mathematics. Newton actually discovered that. Newton discovered that there are very simple mathematical rules which govern the function of the universe. In fact, he could say that he discovered the blueprint of the mathematical blueprint of universe as laid down by Creator, by God. Next week, we're gonna watch a documentary about Newton, and there you will find more and more about his science, his philosophy, and his character. This slide and next slide are just references about life of Newton. I usually don't ask questions about these kind of things, but to have a general idea about this person who is so important in history of human being, he was born premature. He had a very bad childhood. His father died before he came to the world, and his mother married. He had to go to live with his grandparents. He always was sick, and he didn't like at all his mother and stepfather. He studied at Cambridge. He was very brilliant student there. He learned about Latin as a language and Euclid elements and many common books that at that time was the base of education. He learned about Descartes. He learned about Galileo and Copernicus. And he became a professor of mathematics there. But before that, in 1666, there was a plague. 1665, there was a plague in Cambridge, and he had to go to his hometown or his village, actually, and stayed there for a year. And that year is called Annus Mirabilis, or the Year of Miracles. What happened during that year? He discovered the three laws of motion. He discovered the notion of universal gravity, and he invented calculus when he was just 24 years old. What else you want that 24-year can do? So he became a member of Royal Society later, after the invention of a kind of telescope. We're going to talk about it in a short time. And then he wrote two major books which were influential in history of science and history of humankind in general. The first publication was the mathematical principles of natural philosophy, which we just use Principia as an abbreviation. And the second book was Optics. So these two books both created revolutions in physics, and they established physical science in a way that we practice right now. Newton all the life was occupied with religion. He studied Bible very well. He had different editions and different copies of Bible filled with a lot of his own notes at the margin. He rejected this Trinity idea, and he was Arian. He didn't believe that the Father and Son and Holy Ghost are the same and equal. He believed that we have a higher entity, you can call it God, the Creator, and the rest are in lower rank, actually. So he spent a time to discover this God, which in his eyes was a mathematician. Why? First of all, we already again explained about this, we talked about this, that you can doubt about any ideas, any notions, but mathematical presents the absolute truth that you never doubt about that. Always based on our logic, based on the type of reasoning that we have, 2 plus 2 is always 4. 6 is always bigger than 3. There are certain relationships between numbers that never changes. Okay? So this is the absolute truth. And that should be the language of this universe, because God himself in their eyes was the absolute truth. So in one of the questions about Descartes, you see that he involves God in what the existence of this universe and the way that we perceive God. And there you find out that, okay, with this reasoning that we have, with this logic that we have, okay, there is truth in our mind. There are reasoning in our mind that we can find absolute truth. And in this way, we can find God. If otherwise, then what's the story? What you should read Bible, why you should practice religion when your CPU never lets you to find the truth. So we start from a baseline, from a reference point that mathematics is absolute truth, And the creation must be based on absolute truth, based on the order that we see. Okay, the astronomical motions, the universe, you see all these orders, all these laws. Then for Newton, God created the universe based on numbers and weights and based on mathematics, based on geometry. And since in all branches of mathematics, you start from very simple axioms, from very simple rules, and then build a very complicated structure based on that. Newton believed that the same thing happened in the universe. There is a unity, a simplicity behind all diversity that we see in this universe. That was a common idea also at that time, that these ancient books, sacred books in Bible, in Old Testament, God put a lot of truth there, but in a hidden code. That those books are for common people, as we saw in the case of Galileo's letter to Grand Duchess Christina. It's for common people. There are a lot of metaphors, there are a lot of stories, but there are more information and hidden facts in the sacred texts that you have to decipher them and discover them. So they believe that all ancient sages and prophets like Moses, like Pythagoras, they had a better understanding of everything. They knew about all these things. And then we have to go back and find out and decipher the truth of different aspects of this creation through their writings. Newton believed in alchemy, and with his own hand, he wrote 600,000 words about alchemy, not really to pay attention to practical aspects of alchemy, to make, I don't know, gold out of copper. He had an agenda behind. He said that, okay, alchemy is the language of God to create all diversity that we see in, for example, in living organisms, in geology, in stones, rocks, and material and elements around us, because he believed that, again, at the very fine structure of matter, we have simplicity, which imagine in this way that you have atoms, you have particles, and they are very similar particles. You put some of them in some geometrical arrangement, and you make copper out of that. Then you change them and add some other particles. You make gold, or add some other particles. You make, I don't know, tree or a leaf. So he was thinking that there must be very simple rules defined by God, again, to create diversity out of the unity, out of those simple rules. That is why he wanted to discover about this agent of God, which creates what variety of things around us. And again, a mathematician God, an engineer God, in this case, a chemist God, starts from very simple compounds or elements that he have, and by mixing them, he can create whatever he wanted. So look at Newton from his philosophy, from his religious viewpoints, and his cosmology. So Newton's major writings were Philosophia Naturalis Principia Mathematica, or Mathematical Principles of Natural Philosophy. Just look at the title. What's the title? Mathematical Principles of what? Natural Philosophy. And what was natural philosophy that time? Physics. It was in the realm of philosophy. And this guy came to explain what mathematical principles of physics. So he believed that physics has a mathematical base, and it's his job to unravel those. I'm sorry, to reveal those principles. Then his next book was Optics, which obviously about optics, but at the end of Optics, in the second edition, he added some thought-provoking questions, which was not in the realm of optics, but it initiated a lot of studies in 18th century, from first half of the 18th century to up to 19th century. Questions about electricity, questions about heat, about magnetism, about action and distance, and so on and so forth. So if you read Newton's work and read about from Newton scholars, you find this idea that actually Newton followed, his books follows the creation itself. How? When you read book of Genesis, you find out that God created the entire universe. And then what agent made the connection between this universe and human being to see and understand it? Then God created light. So for Newton, there was embedded secrets here, that you create the universe. To do that, to understand that he created what this book, Principia, to find out what were the foundations of this physical universe. And then the agent that made us aware of this creation was light, to see. And so it was very important agent created by God to make this connection, and that it's very important to study. Then he wrote this book of optics, though in the entire two books, he avoids to incorporate religion. In Principia, in the second edition, he added just 1,500 words as general scholium, which there he talks about his theological ideas. But generally, he avoids to mix this, but it shows his mind setting, how to look at the universe and how to make what the his roadmap, or to outline his research project, starting from the physical universe, and then work on optics, and for a long time working on alchemy, which he believed they were agents of God to create this universe as we see. Newton's Principia became a role model for other scientists to do the same thing. And as Newton, by discovery of 3 laws of motion and gravity and application of mathematics, he was able to discover everything. Then other scientists, contemporary scientists, try to do the same thing. Can we discover those basic rules in, for example, electricity, as we see Benjamin Franklin did? Can we apply it to our society and create a sociology based on basic rules? Can we apply it to economy? Can we apply it to life science? As Darwin mentions Newton, that, okay, Newton, by 3 laws of motion and gravity, was able to explain everything in physical world. Can I do it in life science? And you see that, yeah, he followed his masters, this great scientist, British scientist, and did the same thing by introducing struggle for existence and natural selection. He was able to explain this diversity. But I go back, Principia also had this importance, which it contains all previous discoveries. Heliocentric model, not exactly the same way that Copernicus laid down, but in the terms of Kepler. Kepler's planetary rules came from empirical data, just by observation. Kepler didn't have essential mechanics to discover, to find out what is the central force acting in the solar system, in what way it acts. How does a planet move around the sun based on what mechanical rules? He just discovered it by plotting the data that he had. But it was in Principia which Newton proved that the planetary motion must be in that way. It is a simple outcome of three laws of motion and the notion of gravity. So this is the importance of Newton's book, Principia. Okay, I summarized Newton's contributions in these three fields. But before explaining these, I put this image here. This is Aristotle's universe. And you remember, you know better than me, that it had two layers, celestial region and terrestrial region. And we had two different physics, two different motions, two different materials. And even after the time of Newton, many philosophers, many physicists, they believed in such structure. The person who demolished this image was Newton. The person who introduced this idea of universal laws was Newton. Laws that govern from the bottom of the earth to the remotest stars that we see. So it was his idea, and he proved that mathematically and observationally, that if you have, I don't know, a mass of 1 kilogram, and you apply a force of 1 Newton to that, it can accelerate 1 meter per square second, no matter here or end of the universe. These laws were the same as, I don't know, number pi everywhere in this universe. Find a circle, measure the circumference, and divide it to the diameter, you get a number which is 3.14. So this is the physical aspect, but Newton was also happy that he discovered the order by which the universe was created by God. Everywhere in this universe, you find that order laid down by God, by Creator. So this concept of universal laws is so important right now. You are in a lab, you observe the behavior of electron there, and you can immediately generalize it. The same thing happens in a remote galaxy because you observe it. By using a spectrometer, you see that electron at the end of the universe is acting the same way that it acts in your lab. So this was a great discovery, very important. And it was so important that shaped our science after Newton. He discovered 3 laws of motion. Here is not physics class, but you remember that the first law is the law of inertia. Objects keep their state of motion. If they are at rest, they remain at rest. If they are in motion, they continue their motion unless an external force acts on them. This is the first law. That's why we buckle up when we drive. Okay, you stop the car, but your body tends to move. And if you let them move, then you hit the dashboard and things may happen. Okay. Or when you send a space probe to Mars, okay, you just go outside of the atmosphere, set the speed and shoot it in that speed, then shut down the rockets. Then the space probe without any engine continues in that direction forever unless an external force acts on it. The second law is again connected to the first law. When you change the state of the motion of an object, which has mass, obviously, all objects has mass, you have to apply a force. And then force and mass and the change in the state of the motion has a relationship, which we call it what F equals to ma. And the third law is action-reaction law. We don't have exerter force or receiver force. Force always comes in pair with two ends. So you push something, that thing pushes you back with the same force, okay, in opposite direction. That's why we use jet engine, for example. That's why we use rockets and moon. So with these three laws and with the notion of universal gravity, he was able to explain all planetary motions. He said that masses, everything which has mass, they attract each other, and the force between them is equal to the product of these two masses divided by a distance square. It is called inverse square law. Like two magnets, I'm sure that you played with magnets, okay? So you have, say, I have two magnets here, okay? You have two pieces of magnets here, okay? In a distance, imagine their force is 10, okay? 10 unit of whatever you think. When you double the distance, the force becomes what? 1 over 10 square or 100. It becomes 100 times weaker. But when I make the distance half, then the force increases 100 times more. When I make the distance, say, 1,000 times smaller, the force increases 1,000,000 times because 1,000 squares billion. And you have practiced it with magnets. In a distance, a very short distance, force between magnets increases that much, which you cannot control them. So he had this notion of inverse square law for gravity. And by applying three laws of motion, he was able to explain planetary motions. I'll explain about this in the next slide. In mathematics, he invented calculus, and you know better than me that we cannot have this modern science and technology without calculus. Calculus is such a great tool to understand everything in this universe. And he invented the generalized binomial theorem. And in optics, he discovered the nature of color, which nobody knew before Newton. And then he invented what reflecting telescope, which helped astronomers a lot to improve their observations. So let's go one by one. And as far as we can today, we examine some of these notions. So we talked about law of gravity, three laws of motion, and he using these three laws and gravity without using calculus. He was able to produce what? The elliptical motion of planets. There is an old uh, no legend which says that one day Newton was sitting under a tree that year of miracle and reading a book. Then an apple fell down, and at the same time he saw the moon move in the sky, and he said that, okay, the force that brings apple down is the same force that keeps the moon on orbit. I don't think so that it happened, because science never happens in this way. People were thinking about all these things for a long time. It could be, I don't know, a starting point, but entire idea coming in a right package to the mind of Newton, it is not probable that time. Anyhow, even in the what called to commemorate Newton, Great Britain published this stamp with Newton's apple. Anyhow, back to planetary motions. He was able to create planetary motions based on three laws of motion and gravity. He invented concepts like momentum, like angular momentum, like conservation of momentum. He was able to calculate the orbital velocity and escape velocity. That time, nobody was able to think about escaping from Earth, let us think like rocket, but he was able to calculate them. And I intentionally put this equation here. It's not physics class, it's not mathematics class, but your general idea. I'll never ask a question about this. But as a person, as a student in this research institute at UCR, it's amazing idea that 350 years ago, somebody thinks in this way. We know the third law of Kepler. Newton know about that. What is the third law of Kepler? It says that period of a planet is proportional to its average distance. In a mathematical way, p squared equals to a cube. So the period of the Earth around the sun square is equal to the average distance of the Earth from the sun cube. Okay, this is Kepler's law. Newton solved this by using his notion of gravity. And as you see here, he added a gravitational term here. Both sides you see p squared, a cubed, and in between you see this gravitational term. So what's the use of this? Again, think about this. You are studying it 350 years ago. I jump forward and I use a very modern example. We sent the first satellite to the orbit of the Earth, Sputnik, okay? So we sent it, we knew the average distance, we knew about this period. So we knew P, we knew A. Then solve this equation. You know pi, you know G, which is the universal constant of gravity. Then you find what? M1 plus M2. What is M1 plus M2? Mass of Earth plus mass of Sputnik. And since mass of Sputnik is 0 compared to mass of the Earth, then you calculate the mass of Earth as if you put Earth on a scale and calculate that. Isn't it amazing? Very interesting. Or you can jump back, look at satellites of Jupiter. you can estimate the distance of a satellite from Jupiter. You find out A, and you know its period. Okay, just we had enough accurate clocks that time. And then you find out what? The same thing, mass of Jupiter plus mass of satellite. And with very good estimation that you can say that mass of satellite compared to mass of Jupiter is 0, because Jupiter is the biggest planet that we have in the solar system. Then you find out what mass of Jupiter. So it was a great tool that time to find out about details of everything in the solar system without landing there, just by observation and doing some measurements and plug in, and you find out, oh, perfect, it works very well, very accurately. That's why Alexander Pope says that Nathan was just like a messenger who shed light on the hidden facts of the universe. Nathan's first published article, I just explain it and then we can go. This long class makes tired both sides, but there's no other way, sorry. It's just 5 weeks and we are in the 4th week. We're gonna finish it in 1 week, don't worry. His first publication was about what? Light. Okay, so we have this prism here. Okay, you pass light through that, and it breaks light into 7 colors. You experience the same thing when you pass it through light through droplets of water. You see rainbow, and also passing through glass, you see the same thing. People knew about this from the time of Euclid, but they didn't know what happens, because when you have white light, it is white. It's pure white. When it enters into glass, it breaks into 7 colors, and people were thinking that actually glass or water add something to this white light and makes this rainbow. So you see that the nature of question changes here. Nathan asked this question, how about we think that white light itself is composed of 7 colors? Then how can you verify it? First, Nathan passed white light through prism and broke it to 7 colors. Then put another prism in front of each different color to see if he can break red into other colors or blue in other colors. He found that it never happens. So red is pure red, purple is pure purple. Then he said, okay, I collect these colors and then recombine them to see if I can create white color or not. And it happened. The top drawing is by Nathan, his own handwriting. And you see that he passes light through a lens, passing it through, concentrated on a prism, and then breaks it to colors, then combine them with another lens over there, and then passes through a prism and then creates white light. Bingo. The problem solved. After 2000 years of discussing this question, they were able to solve this problem. And in the second image, this modern presentation of this, and you see that, okay, you have 2 prisms, you pass light from one and exit from the other, you turn it from white to colors, and then from colors to white light, and that's it. This is not, this was not only a very important discovery, but also it showed the role of experimentation as something that you perform there and discover about the nature of phenomena happening around us. Again, instead of sitting and philosophically discussing it for weeks, for months, even centuries, you do something and observe the results and then make conclusion. Newton used this discovery to solve the problem of chromatic aberration or color deficiency in lenses. So the original telescopes were using a single lens, and single lens acts like a prism, and it breaks light into colors. Then in early telescopes, we had these colorful fringes around the image. To avoid that, they made telescopes very, very long, with a very long focal length of the objective lens, to make these colorful fringes close to each other. It didn't work. It was very difficult. Newton invented a new telescope in that instead of using a lens, he used a mirror. But what kind of mirror? He used a metallic mirror. He polished silver in a concave shape. Then light doesn't enter into another medium to refract and create these colorful fringes. It bounces back from the surface. Okay? And then you use a similar mirror here and just exit the light here and observe that. So you bypass this chromatic aberration. It is the reconstruction of Newton's telescope. I believe the first one was just 6 inches tall. Then it revolutionized astronomy because astronomers made a Newtonian telescope in which you don't have chromatic aberration, though later we discovered how to combine different lenses to get rid of that aberration. But Newtonian telescopes are cheaper, are more efficient, and better. In this image, you see that Edwin Hubble here sitting in the focal point of this big Mount Palomar Observatory and observing there. Okay. Okay, folks, let's stop here. And on Wednesday, we're going to have, our second writing assignment. And I'll teach 50 minutes at the beginning. Then, like the last time, you will have 2 prompts out of the 3 prompts that I already published. And you have to pick 1 prompt and write 1 essay about that. If you had any question, please communicate with me, and see you guys on Wednesday. If you don't have any question, we end today's lecture.